Okay, so before we get started on our final real new material lecture, I have a few quick updates on the administrative side. So the first one is for the practice final. I did uploaded a key to that practice final exam. Took some time because we graded on paper, so I don't have a key with me. I had to write it yesterday. Nevertheless, so that's the key to the practice final exam. You'll see that because we didn't end up covering chapter 7, the phase diagram and phase rule, the chaperone equation, so you'll see questions in that practice final that's not applicable to you. So for those questions, I circled and say that topic is not covered in my 2024 spring quarter. So you wouldn't need to worry about it for our final exam. That being said, the one phase component or the one component phase diagram is very important material that I really wish to cover. I have also uploaded my lecture notes, and also you have your textbook for your reference. So if you got the time, I highly recommend you to spend a little bit time during the break just to know it, because people will expect you to know that after taking physical chemistry. Just unfortunately, I don't have time to cover it. So that's the final exam. And one additional thing on the final exam, it's more like a study tutorial. So I have the tendency to recycle problems in midterm exam that lots of people have missed. So when I say that, as if you did something wrong in previous midterm exam, I highly recommend you go back and review those questions that you didn't get it right at the first time. Now think about if that question appear again in the final exam, maybe with a different wording or a different equation of state, right? Do you know how to solve that problem? So I that's just a tutorial like I typically do for my final exam. I recycle problems that a lot of people missed in previous midterm exams. And then in addition, so yesterday I was told basically the office hour on Tuesday, lots of people have conflict of other classes. So given that our final exam is next Monday, which is very early in the final week, I'll host an additional office hour on Friday afternoon between 1 to 3 in my Young Hall office. So, it's scheduled for 2 hours. So if you showed up and I'm not there, I might be in my research office. So just send me an email and say, hey, I'm in front of your office. I'll head down in 2 minutes. I'll show up really quick, running in the hallway and so on. But nevertheless, so I will host extra office hour on Friday. So ask me any questions you may have. And as a quick reminder, your worksheet is due on Friday. Your survey is due on Friday. So do make sure you do that before our final exam comes. Okay, any questions before we move on? No? Okay, awesome. All right. So back to our material, right? So this is where we left over. So in chapter 6, right, we started by talking about what is ideal gas mixture. What does the reaction of ideal gas mixture mean? And how do we define equilibrium constant? In our last lecture, we went over definition of equilibrium constant, and we derived the Van 't Hoff equation, which tells us how does equilibrium constant change with respect to temperature. Right. In our last lecture, we also did a problem together, which is doing ideal gas equilibrium calculations. So let's just go over what's the typical process you should be thinking about when setting up a problem related to ideal gas equilibrium calculation. Right. So first of all, these are the equations that are generally true you can use. Right. So the first one is delta G naught equals to negative RT ln Kp. So this one is just generally true for any ideal gas reactions we care about. It's actually true for non-ideal gas reactions as well, but for this chapter, it's all ideal gas reactions. Then we have our definition for equilibrium constant. So these two are just generally true, right? So you can feel safe to use these two equations for any temperature you like, right? So for example, this one, if we're looking at delta G naught at say 4,000 Kelvin. Now my T is 4,000 Kelvin. my equilibrium constant is at 4,000 Kelvin, but the relationship between delta G naught and negative RT ln Kp will always be true, no matter what temperature it is. The tricky part about temperature is how do we get delta G naught, or how do we get equilibrium constant? Now, if we're using the thermodynamic table, right, then we are bound to use the thermodynamic table to get the delta G of the reaction at 298 Kelvin. All right, so the first two equations are just generally true, whatever temperature we care about. But if we're using the thermodynamic table, then we're only calculating the delta G of the reaction at 298 Kelvin. In our last lecture, we went over an example of doing the calculation at 298 Kelvin. The one thing that I don't have time to do a problem with you, but you'll have that in the discussion worksheet, is that what if the reaction reaches equilibrium at a different temperature? Let's say 4,000 Kelvin, right? So what's going to happen? So in this case, you'll first do the tabulated data. Use the tabulated data to find out the delta G naught of 298 Kelvin. And then using that tabulated data, we can use this equation once to get my Kp line, my standard equilibrium constant at 298 Kelvin. So use this equation once to translate the delta G of the reaction at 298 into equilibrium constant of the reaction at 298. But we need to address the fact that equilibrium constant is a function of temperature that will change with temperature, right? So that means we want to use our Van 't Hoff equation as our second step to get the equilibrium constant at a different temperature, right? So let's say if we're talking about 4,000 Kelvin, then we need to tell you how does my delta H naught change with respect to temperature. Right, so in the example question, in one of my practice final, I think, for example, we can tell you my delta H equals to like AT minus like a constant. That's just an example, right? So you can use this equation, plug it into the Van 't Hoff equation to solve for the Kp naught at 4,000 Kelvin. All right, once you have the Kp naught at 4,000 Kelvin, you can come back and use the delta G naught equals negative RT ln Kp again to solve for delta G naught at 4,000 Kelvin. All right, so this is like the cycle we were talking about. You start from 298 Kelvin, you address the temperature differences of equilibrium constant, and then you use that equation again to calculate delta G naught at a different temperature. All right, so this is a quick clarification into what do I mean by like alternative. So this one is just telling you you can use the Van 't Hoff equation to address the temperature differences of equilibrium constant. And then the rest is quite standard. In our last lecture, we went over how to express equilibrium number of mole of species using the ice table, and then how to express your equilibrium partial pressure and use the definition of equilibrium constant to solve for the extent of reaction and solve for the equilibrium composition. So that's something we discussed last lecture, went over an example question together to solve for a numeric answer into like, hey, given the initial number of mole of my reactant and product, and we tell you what the reaction temperature is using the appendix table, we end up solving the number of mole of my reactant and product at equilibrium, right? So that's the example we did together. Now, before we move on into shifts of equilibrium, let's do one more example here. So this is another type of example we can ask. Instead of getting a numeric answer, we can ask you to find out the gas phase isomerization reactions, right? We ask you to express the equilibrium mole fractions A, B, and C in terms of equilibrium constant. So I'll do this together. I'll do it on the board, and we can do it together. If you're watching the recording, the walkthrough is on the annotated notes. So here, what do we have? If we're reading the question together, we should first write down what the question is asking for. Okay, so the question is asking for express my more fractions, let's say chi A, chi B, and chi C, A by equilibrium constant. So A, B, chi K, B, C, and K, A, C. Right, so first write down, what do we want? Secondly, what else do we know about these terms? Like for example, for these terms, what do we know? Using the A as an example, we know that chi A for an ideal gas mixture, that equals to the partial pressure of A divided by the total pressure. All right. And what else do we know? We also know my chi A plus chi B and plus chi C, these are more fractions. We only have 3 species in the mixture, so they must add up to be 1. Right? It's only like a mixture of A, B, and C, so all the more fractions add up to be 1. What else do we know? We have the definition of our equilibrium constant. Right? So if we take my K, A, B as an example, that equals to the product of my partial pressure over P to the stoichiometric coefficient, right, in front. And what do we have? That equals to my partial pressure of A over P naught. A as my reactant, so that's -1. And partial pressure of B over P naught, that's 1. We can simplify this a little bit, right? Because we have my standard pressure will cancel out with each other. We also know my PA equals to chi A times P. So we can simplify our equilibrium constant here to be my chi B over chi A. All right, so far so good. So again, what are we looking for? We're trying to express my chi A as a function of equilibrium constants. Right? So in this case, what do we have? We can do the same for my K AB to my K BC and K AC. And this one equals to chi C divided by chi B. This one is chi C over chi A. So the procedure is the same to get the equilibrium constant as a function of my more fractions. So going back to this original equation, we have chi A plus chi B plus chi C equals to 0. Now, do we have a relationship between my chi A and chi B linked with equilibrium constant? Or from this equation, what we can write is my chi B equals to chi A times equilibrium constant between A and B. Or we can write this one in here. Right, so that's my chi A times equilibrium constant A, B. Same applies to here. So we can write our chi C equals to chi A times equilibrium constant A to C. Should be 1. Right. So what do we have, right? So now if we can take chi A out to be 1 plus K AB plus K AC to be 1, we have what we want, right? We want to express my more fraction A as a function of 1 plus K A B plus K A C. All right. And as a side note, right now you know how to solve this problem. Why don't you think about it? What if instead of A go to B, A go to C, let's say we have 2A forms a B, and then 3B forms a C. So we will be changing our stoichiometric coefficient in this relationship here, but the logic stays the same, right? So we can replace this hypothetical reaction with different stoichiometric coefficient. Can you solve the problem, right? So the logic is the same, but it just can get more complicated. So this is a quick demonstration into something like, you feel like we didn't learn it, but effectively we're just using the basic knowledge we went over, right? Definition of our equilibrium constant. What is Moore fraction, right? Moore fraction adds up to be 1. So these are the fundamentals we're using in solving this question. Okay, any questions before we move on to our chapter 6.6? No? Okay, sounds good. So for chapter 6.6, now we're moving on to talk about shifts of ideal gas reaction mixture. So what do you mean by shifts of ideal gas reaction mixture? So here the question we're trying to answer is considering we start from equilibrium condition, right? So the system itself may be already at reaction equilibrium. And then we're now changing some of the factors of the system. We're changing the temperature, changing the pressure, changing the volume, or adding reactant, adding product, or adding inert gas into the mixture. So what we're trying to do is using the knowledge we have to try to answer the question is how does my equilibrium shift? It's not necessarily a quantitative relationship. It's more like qualitatively, like say increasing the pressure, right? How will that shift my reaction equilibrium? So the whole point, the whole comparison we're trying to make here is a comparison between the reaction quotient and the equilibrium constant. So let me put down the definition of equilibrium constant again. So my standard equilibrium constant is defined as a product of my Pi equilibrium over P naught to the stoichiometric coefficient. Now in the reaction quotient, this Pi here is the instantaneous partial pressure of I. Right, so the difference here is now the Kp naught, in the Kp naught, this one is the equilibrium partial pressure of my component I. And when comparing the reaction quotient with the equilibrium constant, the take-home message or the key here is that whenever your reaction quotient is smaller than your equilibrium constant, we're expecting a forward reaction. When they're equal, we're expecting them at equilibrium, so no change. When your reaction quotient is larger than equilibrium constant, we're expecting a backward reaction. So these are the fundamentals. And then we'll go over several different scenarios and try to derive how does my equilibrium shift when different properties are changing. So again, before we do that, I want to highlight, like, don't try to remember what we derived. Try to understand what we're doing when deriving that, what we're doing to get to that conclusion. Because things can change very rapidly, right? So it's not necessarily always true. Don't try to remember it. Just trying to understand what are we doing? How did we get to the conclusion? So the first question, isobaric temperature change. So the way to think about it is we have two different things, right? We have QP and we have KP. We're trying to find out how does my QP and KP change. Now, typically, when we're talking about the changes, in this class at least, we'll want to make sure only one of my reaction quotient or my equilibrium constant is changing. It's really hard to compare it when both of them are changing. So for example, in this case, when we say an isobaric temperature change, right? So my reaction quotient here, keep in mind, this one is the product of the instantaneous partial pressure. So I'm telling you the reaction quotient is not changing, but why it is not changing? So in here, if you think about it, we have isobaric temperature change. So my PI, the instantaneous partial pressure of each species, equals to chi I times total pressure P. Right? We're not adding anything into my reaction mixture, so and also the total pressure is constant. So the partial pressure of each of my species will remain the same. By changing the temperature doesn't change the reaction quotient. All right, but the reaction quotient is not changing. But when temperature is changing, my equilibrium constant is changing with it. So how does my equilibrium constant change? Is it increasing or decrease with respect to temperature? So that goes back to our last lecture. Remember, we did the plot on the board, right? So how does my ln Kp change with respect to delta H? Right, so in this case, we're trying to say, what is the nature of the reaction? Right, so when my delta H naught is positive, what do we have? So a positive delta H naught means we have a endothermic reaction. So my ln Kp naught will increase with temperature. All right, so when my ln Kp naught increases and my Qp does not change, my Kp becomes larger than my Qp. So we're predicting a forward reaction because my Kp naught is larger than Qp. All right. Alternatively, when my delta H naught is negative, we have exothermic reaction. So my ln Kp naught would decrease with temperature increase. So that means we have a backward reaction because my Kp naught is smaller than Qp with temperature increase. All right, and then you might ask, how do we find out what is delta H? Well, for that, you can use our appendix table. Right, so if we give you a reaction of, say, water decomposed into H2 and O2, can use the thermodynamic table to find out if that reaction releases heat or absorbs heat, and use the delta H calculated from the thermodynamic table to estimate how does my equilibrium constant change with respect to temperature. Or if we put it in words, we have that an increase in temperature constant P in a closed system shifts the equilibrium in the direction in which system absorbs heat from the surrounding. So that's our scenario one. Again, don't try to remember it. It's really easy to get it wrong, but try to think about how did we get it to that conclusion. Next question, what about isothermal pressure change? Right, the same idea. So Q and P, one of them is not changing, one of them is changing. So in this case, what do we have? We have isothermal, right? So something we know is that our equilibrium constant will stay the same, not changing, because the temperature is not changing. And since my pressure is changing, even if the mole fractions are not changing, my reaction quotient will be different, right? So let's compare, write out an expression for equilibrium constant and reaction quotient and compare the dimensionality, which one is bigger. So the example we're using here is say like A, so it's a stoichiometric coefficient A in front of A and B in front of B. Let's say in our initial state, we have P equals to P equilibrium, and then in our final state, we make a sudden change of state so that the pressure is increased to be tripled. Right, so what we can do is write out the equilibrium constant expression. So what does that look like? Equilibrium constant equals to, again, the product of my PI equilibrium over VI. And you write that to be chi A times total pressure over P naught negative A, chi B total pressure over P naught to the power of B. Right. And then what's going to happen after we instantaneously changed our pressure into 3P equilibrium? So this one is just telling you my Kp naught is not changing. So we can write my Qp. That's our product of my instantaneous partial pressure to the power of the stoichiometric coefficient, right? So we have chi A times 3P to negative A and chi B 3P to the power of B. So the size or whether or not my Kp naught or Qp is bigger or smaller depends on if my stoichiometric coefficient A or B is bigger or smaller. Right. So in this kind of question, let's say if my A is smaller than B, so we have less gas molecule in my reactant than product. So A is smaller than B. What we're saying is like this one is like changing smaller than the one on the top. All right, so my Qp will be larger than Kp, suggesting a backward reaction. And vice versa. Or we can generalize this conclusion to say like an increase in pressure at constant temperature in a closed system shifts equilibrium in the direction in which the system volume decreases. Now, what about addition of inert gas or reactant gas or product gas? So in this question, again, we start by saying like addition of inert gas. So in this part, we're setting it up to say like isochoric addition of inert gas so that both temperature and volume are kept constant. An inert gas means that gas does not react with anything. So what do we have here? Now, first of all, constant temperature tells me my Kp naught is not changing. Right. And my constant volume tells me it's ideal gas, right? So we always have PV equals to nRT, or the partial pressure of any of my reactants or product equals to number of mole of that species, RT, divided by volume. Right, so adding an inert gas will not affect the number of mole of your reactant or product. So the partial pressure of your reactant or product will remain unchanged. And since my partial pressure is unchanged, we know that our reaction quotient is the product of my partial pressure to the power of stoichiometric coefficient. It will be unchanged. So the isochloric addition of inert gas into your reaction mixture will not shift your equilibrium. Right. Now I want you to think about one more thing. What if we're talking about the isobaric addition of inert gas? So constant T and P. Right, so for the isobaric addition of inert gas, my temperature is not changing, so Kp still not changing. Right, but what about the partial pressure? Now my partial pressure equals to the mole fraction of each species times the total pressure. So in the case of constant temperature and pressure, addition of the inert gas into the reaction mixture actually changes the mole fraction of your reactant or product, and thus have an effect on the equilibrium. So this is what I mean by like pay attention to reading the question carefully. Don't jump to the conclusion too fast. All right. And let's see one more example to show like the constant volume and constant pressure situation can be very different. So now thinking about the condition of adding the reactant gas. So this part will be a revisit to the Le Chatelier principle that you probably learned either in high school or in general chemistry, right? So in the Le Chatelier principle originally proposed is saying like adding the reactant will push the reaction forward, adding product push the reaction backwards. So we'll see it's not always true. And we need to be very careful when we are stating the Le Chatelier principle. So the first question here we're trying to answer is what if we have this reaction, AB goes to 2C plus D, and we're saying we're adding substance A into the reaction mixture and try to predict how does the equilibrium shift. All right, so in this question, first we'll look at constant temperature and volume. So again, what do we have, right? So constant temperature tells me my Kp naught is not changing. Right, and what else? We also have constant volume. So that tells us we have our partial pressure of any of my species I equals to number of mole of my species I and RT over volume. All right, so in this question, what do we have? Now we're only adding substrate A into the mixture. So the Pi of my B, C, D is not changing. And my partial pressure of A will increase with NA increases. Right. So that means when we're writing out our reaction quotients as a Pi to the stoichiometric coefficient, and we can write that one to be my Pc squared times Pb times Pa minus 1, Pb minus 1. Right, so since my Pa is increasing, my reaction quotient will decrease because that's the stoichiometric coefficient being negative. So my Q will decrease with Pa increase, and everything else stays the same. Now my reaction quotient is decreasing. My equilibrium constant is not changing. So addition of A will push the reaction forward. That fits our expectation for the Le Chatelier principle. So you can use that when we have constant temperature and volume. But for constant temperature and pressure, that's a different story. Right, so this is a constant temperature and volume scenario. And now let's start looking at the constant temperature and pressure scenario. Again, what do we have? For constant temperature, we know that Kp naught is not changing. All right, and for constant pressure, we have the partial pressure of your species I equals to the mole fraction times the total pressure. Now, if we use our ammonia formation as an example again, so we have one N2, obviously gas phase. So N2 plus 3 hydrogen goes to 2 NH3. And we can write the expression of our equilibrium constant and our reaction quotient using the mole fractions here. So this part is just a simplification of the original definition of partial pressure, since partial pressure just equals to mole fraction times the total pressure. Total pressure is a constant. So we simplified the expression for equilibrium constant and reaction quotient. So let's look at some case study here and try to see what it means when we say the Chandelier principle does not necessarily apply. So do the case study first. Let's say at equilibrium. Right, so at equilibrium, I'll first give you the number of mole of my NH3 at equilibrium equals to 1.00 mole. Number of mole of N2 at equilibrium equals to 3.00 mole. Number of mole of H2 at equilibrium equals to 1.00 mole. So we can calculate the mole fraction because we need that to calculate our equilibrium constant. Right, so my mole fraction of NH3 at equilibrium is 0.2. That for N2 at equilibrium is 0.6, and my H2 at equilibrium is 0.2. Right, so we can calculate our Kp naught, or Ki naught, it doesn't really matter, to be 0.2 squared. So my NH3 has like stoichiometric number 2 over 0.6 times 0.2 cubed. You can plug in that into your calculator to get 8.333. That's our equilibrium constant. All right. So now we'll do two examples. So in scenario 1, we're adding, say, 1 more of N2. So that's our scenario 1. We're adding 1 more of N2 of our reactant into the mixture. So we have, well, NH3 instantaneous equals 1.00 more. Number of more of N2 that now becomes 4.00 more. Number of more of H2 equals to 1.00 more. And to get my calculator out, and we can do my mole fraction of NH3 in scenario 1. That equals to 1 divided by 6.167. Mole fraction of my N2 in scenario 1 is 4 over 6. That's 0.667. That of H2 in scenario 1 is 1.167. Right, so for my scenario 1, we can calculate my Q to be 0.167 squared, 0.667 times 0.167 cubed. And just doing that calculation, we have 0.167 squared divided by 0.667 times 0.167 cubed. And that's 8.978. Yes.
For KP naught, you always usually have the, it's over like P naught, which is just one bar.
Right.
But here, you're just.
Yeah, that's one of the. So in this case, we're just saying like these two are effectively the same thing. Our total pressure is not changing, so it's going to cancel out. So I do agree the definition of reaction quotient in your textbook is a little bit problematic. If I'm writing it, I want to. I typically will write it as like QP, as like a product of my instantaneous partial pressure over P naught to the stoichiometric coefficient. So there, it is a little bit problematic. I might update my note later on, but in this case, it doesn't matter. Okay. So, coming back to what do we have? So now, in this case, we calculated our reaction quotient. And if we're comparing our reaction quotient here, we have my reaction quotient to be larger than my equilibrium constant. And what does that mean? So that means we have a backward reaction. So addition of my N2, which is a reactant gas, is actually pushing the reaction backwards. So that means we want to revisit our Le Chatelier principle a little bit, right? So instead of using the number of mole that's being added into the reaction mixture, now the rephrased Le Chatelier principle is that when the system is at equilibrium, a change in one of the intensive variables. So now what's the difference here is we're replacing the number of mole, right? Addition of number of mole of reactant or product. We're replacing that to the change of the mole fractions. Right, so we're talking about the mole fractions changing, and we want to make sure the equilibrium will shift back to counteracting that change of the intensive variable. So not the number of mole, but the mole fraction. So I'm running out of time. I don't have time to go over this practice problem, but that's all the new material. So in our next lecture, we'll do this practice problem together and also go over a review of the entire quarter. But before we do that, I can go over like how do we set up this question? Right, so this is a textbook question. It's basically said we give you an ideal gas reaction. And can you quickly state whether the equilibrium will shift to the right, to the left, or just stay where it is for different scenarios, like temperature change at constant pressure, volume decrease, constant temperature, some reactant being removed, some helium is being added, etc. Right, so how to approach this question? So to answer this kind of question, I highly recommend you first remind yourself in what are we comparing? Right, so we have, again, my equilibrium constant. We know it's a function of temperature. So what does that mean, right? So it's a function of temperature. We're using our Van 't Hoff equation. So d ln Kp naught over dt equals to delta H naught over RT squared. Right, so if the temperature is not changing, your equilibrium constant is not changing. If the temperature changes, then depending on whether the reaction is exothermic or endothermic, you have different dependence of temperature of your equilibrium constant. And you can get the delta H by looking at the appendix table. Now for your reaction quotient, we have that equals to the product of your partial pressure to the stoichiometric coefficient, right? So then you have two different scenarios. If we have constant volume, then your partial pressure will equal to number of mole of that species, RT divided by V, right? So if we're adding inert gas into our reaction mixture at constant temperature and volume, then this tells you it's not doing anything to the equilibrium. Alternatively, if we're looking at constant pressure, what are we having? We have Pi equals to chi I times total pressure. So that means you want to look at the mole fraction of your species when the pressure is kept constant. Yes?
If there's a change in temperature, can we assume that the delta H naught is constant? Or do we assume that's also changing?
Well, so in this question, typically we don't, so for this question, it's very qualitative, right? We're just trying to ask you which direction it moves. We're not asking you how much it has been changing. So for delta H, if you calculate it to be a negative number, you can assume it's going to stay negative, whatever temperature range we're talking about. Right, so delta H will change with respect to temperature, but the sign of delta H of the reaction is unlikely to change unless our temperature changes like a million K or something. All right, and at the end of the day, you can compare your reaction quotient with equilibrium constant. Right? Reaction quotient smaller than equilibrium constant, forward reaction. Reaction quotient larger than equilibrium constant, backward reaction. So that's a general approach to answer this kind of question. We'll go over that one by one in our next lecture. And also in our next lecture, I'll do a chapter end review. Basically, let's go over all the topics we covered in this entire quarter and try to demonstrate like how are these topics connected with each other, right? What is behind all the math, what is behind all the derivation that we went over together this quarter in physical chemistry. And well, that's all from me. That's all the new material you need to know preparing for the final exam. And again, I will be hosting extra office hour on Friday afternoon. You have your discussion worksheet due this Friday night. So do keep in mind on those due dates. And also do make sure you submit your survey and our course evaluation. I'll see you on Friday.